everyone, I am Samyo Hangma Rai, and today we're going to study the chapter titled Yes, You Can Boil Water at Room Temperature of grade 10. So let's begin.
Yes, you can boil water at room temperature. Sometimes it's right on the box of rice mix, the high altitude version of cooking instructions. Usually this means that your rice will have to cook a little bit longer if you are in Denver or at the top of Mount Everest. Of course, that's just a joke. No one cooks rice at the top of Everest, but why are the instructions even different? Why does it matter where you cook? The answer has to do with boiling water. You ask some people on the street about the boiling temperature of water. Some might say 212 Fahrenheit or even better 100 degrees Celsius. But that's just not always true. As you increase your altitude above sea level, the boiling point of water decreases by about 1 degree Fahrenheit for every 500 feet increase. That means your water in Denver is going to be 203 degrees Fahrenheit, and this will have an impact on your cooking. But why? Water vapor pressure. There are many awesome things about water, and one interesting factoid is that on the surface of the earth, you can find water in all three phases: solid, liquid, and as a gas. We call the gas phase of water water vapor. You might think that you need to boil liquid water to create water vapor, but you do not. You just need some liquid water at room temperature. Picture a glass of water. If you could zoom in with supervision, not actually possible, you would see that this water is made up of a bunch of molecules, water molecules. Although these molecules are themselves made of 3 atoms, 2 hydrogens and 1 oxygen, let's just think of them as tiny balls. These tiny water balls are moving around in the water but stay fairly close to their ball neighbors. This motion isn't due to currents in the water. Instead, this is thermal motion. Imagine these tiny balls jigging around in a giant collection of balls. The hotter the water, the greater the motion of these water balls. But wait, the speeds of the water particles are not all the same. Although there is an average ball speed, some are going faster and some are going slower. It's just like the height of a group of adult humans. There is an average height, but everyone is not the same. Some people are very tall, but that's just a small fraction of the total group. If you have a glass of water sitting out on a table, the water balls don't just stay as a liquid. Some of these balls have enough thermal energy to break away and become free. Free from the liquid stage means the water ball is now a gas, water vapor. Boiling is not needed to get this water vapor. But wait, it works the other way too. Some of the water balls in the gas stage can interact with the liquid water and join the liquid water balls. Water in a closed container will eventually reach an equilibrium state between water vapor and liquid water. At this equilibrium state, the rate that water balls are freed from the liquid state are the same as the rate of water balls entering the liquid state. The pressure of this water gas in equilibrium is called the vapor pressure. You can see evidence of this water vapor in a closed container by looking at the water that condenses on the walls. Boiling water. Here is what water looks like when you get it to 100 degrees Celsius in slow motion. Yes, I know you have seen this before, but it's still cool. What are the bubbles in the boiling water made of? Are the bubbles made of air? What about some hydrogen and some oxygen? No, the bubbles are water vapor. There are small pockets of water in the gas phase. I mean, they could not be air. Where would this air come from? The only option is that the bubbles are made of water vapor. So, what is happening to make these boiling bubbles of water vapor? It's all about temperature and vapor pressure. As the temperature of the water increases, the average speed of the water particles also increases. At some point, water molecules have enough energy to push back other water molecules in the liquid phase to form a bubble. But you have to have the water hot enough so that the particles are moving. But wait, it is also about the vapor pressure. In order to keep the bubble from collapsing, the pressure inside the bubble must be equal to the pressure outside the bubble. Inside the bubble is the vapor pressure and outside is the water pressure. This means that for water to boil, the temperature must increase until the vapor pressure is equal to the outside pressure and a bubble can form. What about that external pressure? That depends on 2 things. First, water itself. In order for the water not to collapse, the deeper water must have higher pressure. So, the water pressure depends on the depth, the density of water, and the gravitational field. For a typical glass of water, the pressure at 2 centimeters below the surface is only a 2.0% increase over the atmospheric pressure. And that is the second thing that contributes to the total pressure, the atmosphere. The atmosphere also pushes down on the surface of the liquid to increase the pressure in the liquid, lower pressure. What if I decrease the atmospheric pressure pushing on some liquid water? This would reduce the pressure in the liquid also. If I reduce reduce this pressure enough, I can bring it down to the same level as the vapor pressure. Boom! Now the water particles have enough energy to form the tiny little boiling bubbles without the need to increase the temperature. I can even get the water to boil at room temperature. Yes, you need a vacuum pump and a strong container to get this to work, but you can do it. Notice that I hold onto the boiling water flask just to prove that it's not hot. Wait, you don't have to trust me. You can do this on your own. You just need one of these large plastic syringes, get the syringe and put some water in it with very little air. Now, seal up the end and heat up the water just a little bit. Here, you can see my version. I use hot glue and a rubber stopper, along with a Lego piece, to seal the hole. The syringe was then heated to about 42 degrees Celsius, a little over 100 degrees Fahrenheit. Now, I can pull the plunger out to decrease the pressure in the liquid and induce boiling. It is pretty tough to pull the plunger back to decrease the pressure, but you can do it. Oh, why the heat water up? Well, I cannot get a perfect vacuum by pulling the plunger, so I need a little boiling help by starting the water at a higher temperature. This is exactly what's going on when you cook your rice at high altitude. Well, not exactly the same. There is not a human pulling back on a giant plunger that holds the air on Earth. The Earth's gravitational field does that for you. By Rhett Allain. Number A, find the words from the text that have the following meaning. A, the height of an object or point in relation to sea level or ground level altitude. Number B, a group of atoms bonded together, molecules. C, a state in which opposing forces are balanced, equilibrium. D, to change from a gas or vapor to a liquid, condensed. E, a piece of unreliable information that is repeated so often that is accepted as the fact, factoid. F, a space or container from which the air has been removed, vacuum. G, a device that is used to remove blockages from the drain of a basin or tub, plunger. Number B, complete the sentences with the correct words or phrases from the text. A, water bubbles break down if vapor pressure inside and outside the bubbles is equal. Number B, as the altitude goes up, the boiling point of water decreases. C, random motion of molecules or particles is called thermal motion. D, if the door does not open, try pushing the key in the lock. E, certain chemicals can induce undesirable changes in the nervous system. Number C, answer the following. A, what is the speed of water particles compared with? The speed of water particles is compared with the height of adult humans. B, how are bubbles formed in boiling water? Bubbles are formed when water molecules have enough energy to push back other water molecules in the liquid phase. Mention two things on which external pressure depends. External pressure depends on the density and the depth of water. Homework. Number D, how is the atmosphere related to the pressure of water? E, what would happen if the atmospheric pressure on the liquid water was decreased? F, what would the experimenter gain if she or he pulled the plunger out? How was your class today? If you have any feedback or suggestions, please feel free to email us at learning@deerwalk.edu.np. See you in the next class. Thank you.